The subject of this presentation is a shading tool we have developed at ATI, and the code name is ASHLI, which stands for Advanced Shading Language Interface. I'll start with a rather simple-minded background review, talk about some of the internals, and conclude with a demo. So recent development in graphics hardware have made it quite favorable to play a role in digital content creation. Nevertheless, there still remains an interface disparity between what an artist is accustomed to and the shading contracts that the hardware is using. Bridging this void is ASHLI's main motivation. Much of the goals we have set forth for ASHLI are fairly intuitive and rather obvious, but there is one which is virtualizing the hardware, which might not be initially. Later on, I would have liked to make the case that it need not take just a complex shader to overrun the resources of the hardware. And in fact, I'm hoping that this will make rational to our significant commitment to support multipassing in this tool. ASHLI on its input is multilingual on the input side. We have implemented a modest subset of the Renderman shading language, and recently we have added support to the OpenGL shading language. ASHLI operates on a program entity, which is a collection of shaders. A surface shader is mandatory, and any of displacement, light, volume, or images are an option. Shaders can be instantiated, and this is very handy when you deal with a light with multiple light sources. A shader instance is just a lightweight memory footprint of a shader, and a user can initialize its input formals to any desired values. ASHLI embeds a compiler technology, and as such it has a front-end and a back-end component, which I will touch on its specifics a little later. We realized upfront that by translating a high-level abstraction of shading construct down to hardware level, it will take us many intermediate representations. As a result, the shading pipeline that we have in ASHLI is rather deep. As I mentioned before, complex shader, and essentially any of them who overruns hardware resources is being segmented into chunks that fits the constraints. In addition to the segment, on a per segment, we also emit metadata, which we term formals, and this is useful for providing runtime appearance control to the application. This data comes in terms of shading state, setting, and texture binding. Finally, on the output side, we emit code that is for both the OpenGL and the DirectX platform in the variants that currently are available. ASHLI to an application is essentially a shading coprocessor. It has a very definitive task, and it offloads the application in that regard. The application will hand in a native shading description, and ASHLI will emit on a per segment base the metadata that we talked about previously and the hardware shaders. From there on, the application needs to take this data and commence multipass rendering and essentially bind the shaders and the textures to the geometry. This slide depicts the ASHLI shading pipe. I will touch briefly on any of the stages and later on talk a little bit in detail of a couple of them. So initially, every shader gets parsed and converted to an abstractive tree data structure. Then we expand all the instances of the shaders and we fold them into one. We fold them into one in a prescribed manner where displacement will come first and volume will come right after the surface. At this stage, functions, both the built-in and the custom, are still being maintained apart. Then we go into the shading rate stage, for which a program or pieces of it are being mapped onto the GPU processors, and this is either the vertex or the pixel. For the Renderman program, we do it implicitly. All the program maps onto the fragment shader, and we have an option to generate a matching vertex shader inside the shading rate stage. In addition, we can take also explicit vertex and fragment shader, and this is useful for the OpenGL shading language. Up to this point in the pipe, we have faithfully represented the syntactual structure of the incoming language, or shader. Now we move on to the simplification stage, where here we essentially take every statement in our tree and we convert it into a simplistic assignment statement that on the right-hand side has a single expression node with a dyadic operator. This simply maps onto a hardware instruction much easier. We inline all the functions and we unroll the loops, and at the end we get an expression tree that represents the whole program, one for each of the GPU processors. We then move on to optimization, and here what we do is that we remove all the dead code, we fold all the constants, and we conduct live range analysis on registers. And whenever possible, we take scalar variables and map them and pack them into vector registers. Finally, the multipass is where we evaluate the tree against the hardware cost, and if need so, we break it into a sub-trees. Each fits into the hardware constraint cost that we have. At the end, we emit target code, and this is for both the OpenGL and the DirectX. The metadata is invariant to this extent and has the same single format. On the API side, it's rather simple and very extensive and portable. There is only one point that I wanted to touch on this subject, and it has to do with the fact that built-in functions for Renderman and OpenGL are, for the most part, maps onto an arithmetic expression or a series of those. But there are a handful of those, like the noise and ATAN, that we map onto procedural textures. Those procedural textures have to be present whenever the shader is run under rendering. To assist the application, ASHLI will generate on the fly those procedurals, and an application can simply query the texture data and go and download it. On the folding side, I only wanted to touch on one thing that is very typical for Renderman, and this has to do with unrolling light emission and light integration constructs. Consider the case where we have a program which has 3 instances of a spotlight. In this case, and the lighting model has both a diffuse and a specular component. In this case, what ASHLI will do, it will hit first the diffuse component, and it will expand on all the light instance code. It will follow on with the integration for the diffuse. And then when it hit the specular one, there is no expansion anymore. It will simply reuse what have been expanded in the previous integration construct. Now, so if somebody extended to many tens of light and 100ths of light, one can see the amount of savings that we get by doing this kind of optimization. Now, previously I'd mentioned that I wanted to make the case that it's not necessarily to have a complex shader to overrun hardware resources. Now, consider a simple-minded Renderman shader. And in a generic fashion, it will have the current position, either the position in current space or transformed into shader space, which is already one variable. And then it will have, and usually you would want a face forward and normal, and this will require a normal and an incident vector. And obviously you might use the current texture coordinate, which is the S and T. Now, to this extent, we have already used 4 out of the 8 varying variables that transfer between the vertex shader and the fragment shader. So, and this is essentially a very simple-minded shader. So just imagine that if you would add onto it a couple of generic light shaders that are using their own shader lookup and casting shadows, then you have immediately exhausted all those varying IOs that go between the vertex shader and the fragment shader. So this is why we believe that multipass and essentially making it seamless to the application is very valuable and very important in our implementation. The technique that we use is the one that Eric Chen has just presented. And again, from an application standpoint, what it has to do, it has to allocate floating point buffers to store those intermediate results, and this is all for the sake of preserving the precision. In addition, while it seems like that on the surface we might incur overhead in doing the multipassing, it's not necessarily the case, because you may be shading a fragment or bound already, and then the additional cost for doing the save and restore may be still a negligible part of the overall shading that you have to execute. I wanted to touch a little bit about imaging. It is a convention that in software renderers, filtering operations are done in line with the rendering. We wanted to expand ASHLI to perform imaging operation post-rendering and give essentially the same functionality. So the program modality coming into ASHLI has an optional displacement program, and then for this we use a null surface. And then there is a mandatory render program which uses a surface shader and optionally light and volumes. And then we can cascade a series of imaging programs, and for each we can essentially perform an image operation. This allows us to do both point and area filtering, and what is happening is that the image at the output of each, the rendering or any of the image programs, gets basically pushed from one stage to the other as a texture input to the next program. Finally, I wanted to show the formal's metadata format. It's rather simple. It has a vertex and a fragment session in it. All the varying variables that are going from the vertex to the fragment are shown, and they have to match. And then all the uniform state is mapped onto constant registers. As you can see, we are making a great deal of effort that if there are scalar uniforms, we map them onto a vector register type, and we pack those. And then for the textures, we have all the sampler registers that give enough information how the application should bind textures. Now we will go and we'll show a quick demo. So this is the ASHLI viewer, a tool that we use to validate the shaders that we emit. On the left pane, you see the program, and in the middle pane, you would see the source shader that we are using. This is in the Renderman format. And the first shader that we wanted to show here is the red apple shader, the infamous one from Renderman. And here, this one has generated 4 passes with a little bit under 200 instructions. It automatically brings the sliders that represent all the input formats to the shader. And you can see as we move them, like the transform ones or the ones that affect the appearance of the apple, that gets pretty much in real time. We can also modify the light attributes and change the light behavior on those. And it's fairly smooth to this extent in a real-time fashion. Now on the right-hand side, you could see the generated code, and this is for both, and you can see it for every pass. You can see the generated fragment shader code. Similarly, you can see the vertex shader code as well. Next, we will move and we will show the shadow capability that we have, and also to demonstrate that in real time. So this example has a wood shader, and it's being lit with 6 light sources, where 2 of them are casting shadows. Then again, what you can see is that we can essentially change the position of the lights, and we can immediately get a reaction to it. Note that every time that we change the position, we essentially generate a new depth map, and this is all done as we speak. Finally, we wanted to show some of the image processing capabilities that we have. And the first one, we will show a waves type of filter. So here, what you can see is that this is the geometry that we have. And now we apply some frequency and some amplitude changes to the wave filter. And note that we can rotate or transform the position of the the 3D object, and we can get immediately response about the image processing that we apply to it. Next, we will show in the same manner two image operations that are happening in a cascade manner. One of them, which is the waves that we just shown, and the second one is the edge detection. And then again, you can see that we can rotate it right away and we can get an immediate result. This can obviously be extended to almost any operation or any image operation that you would want to conduct. Okay, we can get that. To conclude, just some forward-looking statements here. We obviously would want to look up other shading languages as they emerge. We want to extend the shading rate capability that we right have, and we also would want pretty much to stick with the multipass technique that we have and extend it. The ASHLI demo that we have just presented is available for download at this site.